Okay, Chapter 3, Sequential Logic, Part 2, Propagation Delay. Let's say you've got the following circuit. This was two logic gates, an inverter and an AND gate. And you were given the diagram of A and asked to draw the sketch what the response of B and Q would be to that input on A. Have a go at it. Give yourself a minute. Do pause the video. Okay, so hopefully you've drawn something that looks like this. So this is B. B was an inverter, so it's the opposite of A. You would, in the exam, obviously get a graph paper to do this, so it wouldn't look nearly this messy. And Q is an AND gate based on A and B. Obviously, Q is an AND gate, so it only goes high if they're both high. So at the beginning, A is low, and in the middle, B is low, and at the end, A is low. So it's 0. Nothing happens. Okay. However, the truth is that there will be a propagation delay. There will be time for B to adjust to A reacting. So A starts low, and B is obviously high, and then for a moment and very short amount of time, we're talking nanoseconds, B will not have reacted to A going high. Then you give it a moment longer and it will react. So this is called the propagation delay. And this is true in all circuits. Just takes a moment or two for it to respond. So with this in mind, try and sketch the response of B and Q again. Again, pause the video and have a go at it. Okay, so hopefully you got something like this. This is B, and this is the delay of 5 nanoseconds. So notice that it's taking B 5 nanoseconds to respond to the fact that A is changed. So during this time, it hasn't had time to respond to the fact that A has gone high. It's now realized and it's gone low. And again, it's taking 5 nanoseconds for it to respond and go high again in response to A going low. So what does that mean for Q? Well, that means that for Q, for a short period of time, and it is very, very, very short, it believes that they're both high. So that means it will go on, because it's an AND gate. And this will only happen after the fact, because it takes Q a moment to actually realize that B has gone on as well. And so it will look like this. So this is a very short pulse. So this is 5 nanoseconds long, which is a very short amount of time that it will be on for. Your picoscopes, for instance, would struggle to measure this. But it is on. And this is called a transition gate, well, transition circuit, this kind of setup. In the exam, you may well get one which has multiple inverters on it. So I've seen one where they put 3 on it into an AND gate. It doesn't have to be going into an AND gate, it could be going into a NAND gate, it could be going to an OR gate or something else. So those kind of circuits, you will be expected to be able to draw these diagrams and the response of the circuit. You could be asked to design a transition gate with a particular delay. Each inverter adds a 5 nanosecond delay. So if you need a delay of 15 nanoseconds and each one does 5, then you'd need 3 of them. You will need to read the question because sometimes they have different amounts of propagation delay assumed. So in this case, I've looked at 5 nanoseconds, but that could easily be 10 nanoseconds or 8 nanoseconds or whatever. It does depend a little bit on, in reality, it depends a little bit on the chip, the manufacturer, and the type of logic gate. Some are slightly quicker than others. Okay, what's the purpose? Why do we bother with this tiny, tiny pulse? The purpose is synchronization. So we're going to look in the next video, when we take the S bar R bar latch a little bit further, at the SR latch, which is a circuit that looks like this. And the SR latch has a synchronization of a clock here. And basically it only reacts when the clock is high. The problem is if the clock is a standard astable, so it's, let's say it's a Schmidt inverter astable where the marked space ratio is 1:1, it's high for a lot of the time, which means that the synchronization isn't that good, because it's been triggered for quite a long period. And that means that multiple changes in the input may well get recorded, and that can mean that different latches get out of sync. So instead what we do is we put something like a Schmidt inverter as our input pulse, but we put that through a transition gate, which means that it will react only to the rising edge, or sometimes the falling edge, depending on what you want, and it will give a very short pulse in that sort of 5 nanosecond region on the rising edge. Which means your synchronization is much better because it's giving a very, very short period of time to read what's happening at set and reset, and therefore if you've got multiple latches, they're all reading it at a very particular point in time. So it's really about synchronization. So that's the purpose of this. In the exam, if they ask you what's the purpose of a transition circuit, and they've asked you to analyze one, then asked to give the reason, you just need to say that it creates a short pulse for synchronization. Okay, that's it for transition circuits. Do make sure you're comfortable with the graphs, as you will be asked to draw them in exercises and in the exam.